have in this session is on public randomness extraction with ephemeral roles and worst-case corruption by Jesper Busch-Nielsen, Maciej Obremski, and Joao Ribeiro, who's giving the talk.
Yeah.
Enjoy.
All right. Yeah, thanks, Christoph. Welcome everyone. So this was a really fun project with Jesper from Aarhus and Maciej from CQT and the National University of Singapore. So let me just start, with the very basics. Everyone knows that, cryptography fundamentally requires randomness. And so it's important to think about how we generate this randomness, like the type of randomness that we need. And sometimes we even need, types of randomness where, several parties need to agree on a common string, and they need to trust that this string is indeed uniformly random. And one very obvious solution for this is to maybe assume that there's some trusted randomness generator in the sky that just samples random bits, broadcasts them to everyone. And here, of course, then everyone agrees on the same bit, and they all trust that this bit is indeed uniformly random. This, of course, is a very strong assumption. We'd like to weaken this. So we usually replace this by some distributed protocol where parties interact with each other to agree on a common bit. But it is also very complicated because most of the protocols for this task kind of require you to maintain a stateful environment for a very long time. And this is challenging because, for example, there can be some power outage that maybe some computer goes offline, or another computer decides to restart, start installing some updates. And it's even worse if there's an adversary involved, because this adversary can maybe mount some targeted denial of service attacks. And this motivated this notion of stateless multi-party computation, where the goal is to design protocols that don't require parties to keep state throughout the protocol. And a very specific, sorry, let me just hide this. All right. Yeah, so one very recent model for this is what's called YOZO. So you only speak once. And this is going to be also the focus of our work. And YOZO, so it's a model for stateless MPC. And protocols here are composed of a series of roles that are activated in sequence. And the way I think we should think about this at a high level is that there is a large ground set of parties, and there is a role selection mechanism that picks a party to execute a certain role. And executing a role basically means that you can broadcast a public value, and you can send private messages to future roles. And after the party executes this role, it can go offline forever. It could blow itself up and never speak again. And that's perfectly fine because parties don't have to keep state. So for the second role, the selection mechanism picks another party. This party executes the second role, broadcasts a public message, sends a message to the future, and so on. All right. And usually what we think of is that this part with the role selection mechanism, this large ground set of parties, is abstracted away. And in the original work, it was just assumed that this is uniformly random, and they use this to do some very cool stuff, including secure MPC with close to half corruptions. And the reason for this is that you can think of, if there are like worst case corruptions or chosen corruptions on the ground set of parties, since the selection mechanism is uniformly random, you're going to see random corruptions of roles. So this is something they use. All right, so onto our work. So the main difference with respect to our work is that we basically replace these IID random corruptions of roles by static chosen corruptions. Okay, so again, here's an example. Here's 4 roles for a protocol. Before the protocol starts, we allow the adversary to corrupt, say, 2 roles of his choice, and the protocol proceeds as before, right? So role number 1 broadcasts a public message, sends private messages to the future. Second role does the same thing, but now it's corrupted, so it can deviate arbitrarily from the protocol, and so on. Okay, so I guess one question is, right, so we consider this problem of public randomness extraction, or you may call it also public coin tossing. And the goal here is that we're going to take these public values, x1 through x4, and we want to apply a deterministic function and compute a coin that should be statistically close to uniform. Okay, and why do we care only about public values is that we also want that people that did not participate in the protocol to also be able to just look at the transcript and compute the coin by themselves, so that more people can have a shared random bit. Okay, so naturally, we can ask, why do we care about worst case corruptions in this setting? I think one natural motivation is that the role selection mechanism may actually not be perfectly uniform. It may be biased towards the adversary at certain points. And we think that worst case corruptions kind of capture this nicely. Second is that studying chosen corruptions in this setting kind of forces us to go beyond some round-based or committee-based MPC techniques. Third, we actually think this is a very clean model that probably find more applications in the future. And finally, there's also some close relationship to other previous works in randomness extraction that's going back maybe 50 years. All right. So I guess one thing that I need to kind of spend a bit of time on is that we need to kind of describe how these messages to the future are implemented, because this affects the adversarial model. Okay. So in this talk, we're just going to focus on one specific setting. We actually have more settings in the paper. But the idea is that we have models that are inspired by some concrete implementations of this mechanism. And we're just going to assume that the adversary learns incoming messages to a corrupted role only when this role is executed. So in particular, if you have role number 1 sending a private message to role number 4, and role number 4 is corrupted, then when the adversary is controlling role number 2, you won't know this message. Okay? All right, so how could this be implemented in practice? Well, you can pretend that, maybe roles share some public key secret key pairs. And the secret key can be maybe secret share over a committee. And when this role number 4 would be executed, this committee reconstructs the secret key to this role number 4. And now role number 1 can just encrypt something, some secret message under the public key. And then role number 4 can just decrypt. Okay. All right. So I guess our main question that we try to understand here is, what is the maximum corruption rate that still allows us to do low bias randomness extraction or low bias coin tossing in our setting? Okay. And so we can basically start by trying to see what we can get with a very simple, probably the most basic approach we could think of. And probably for us, the most basic approach is to take something that we understand quite well, which are round-based MPC protocols, and try to naively translate them into YOZO protocols. So let's say we start with some n-party R-round protocol for delta corruption rate. We can just emulate naively the rounds in the YOZO setting. So basically, for each party, we have R roles, okay, and we have R blocks, and each block basically emulates a round. So first block would emulate the first round of the protocol, and you could just use the private messages to basically pass state to the next round, okay? Then you just emulate all the rounds, and you get a protocol, but there's a problem, because note that the number of roles went from n parties to n times R roles, but the number of corruptions needs to stay the same, because you need to assume that if you look at the chain of roles that corresponds to a party, if you corrupt one of the roles in the chain, you basically have to assume that you corrupted everything. Okay, so number of corruptions stays the same, number of roles blows up, so the corruption rate that you tolerate decreases from delta to delta over R. Okay, so for concreteness, if you try to apply this to see what we can get, so let's say we have a round-based protocol for 3 rounds and 1/3 corruption rate. Then you basically get a YOZO protocol that's secure against a roughly 1/9 corruption rate. Okay, so that's our baseline. And we'd like to do better, right? And that's exactly what we do. So we have both positive and negative results. So in terms of positive results, we basically get some zero-error randomness extraction protocols against T corruptions with 5 T roles, which gives you a corruption rate of about 1/5. Or we also have a stronger adversarial model. We get corruption rate 1/6. And to complement this, we also get an impossibility result that says that if you want to do low bias randomness extraction against T corruptions, you cannot do better than corruption rate 1/4. Okay, so it's a very interesting open problem to try to close the gap between these two results. All right, so let me go and try to explain the main ideas behind our positive results. And I'm just going to present here a slightly suboptimal version of our positive results. So I'm going to give you a protocol that is secure against T corruptions with 5 T plus 2 roles. And then in the paper, we can actually show how to save an extra 2 roles from there. All right. So the main idea in just one sentence is that this is a YOZOfied version of Uli Maurer's verifiable secret sharing scheme from his Secure MPC Made Simple paper. And here's how it works. So we basically have, again, 5t plus 2 roles. We split them into 2 batches. So the first batch we call the samplers. There are 3t plus 1 samplers. Second batch we call the publishers. There are 2t plus 1 publishers. And the high-level idea is the following. So we're going to use subsets of samplers to basically commit to values, so random values, and then send them to the publishers. The publishers literally just broadcast whatever they receive. And then we just take some careful majorities and you XOR everything together, and you're going to get a random bit. All right, so let me explain this in a bit more detail. All right, so the way it's going to work is that we're actually going to do a procedure that works in parallel over basically all subsets of size 2t plus 1 of samplers. And the reason why the 2t plus 1 is because then we get honest majority. And here's how it works. So the first party in the set samples a random bit, forwards to everyone, to all the other samplers. And the second sampler basically forwards what he got to all the other samplers, etc. And of course, we may have corrupted samplers. And if a sampler is corrupted, it may choose to lie and send different bits to different parties or to different roles. So we need a consistency check to make sure that, everything is going OK. And the consistency check is pretty simple. So a role just looks at everything he got and just checks if they're all the same. Because if they're not all the same, then there was some adversary corrupting things. And so we can, if this happened, then you can just say, OK, I'm complaining about this set, and this set is no good. There's an adversary. So the procedure just supports. Otherwise, if they're all the same, we can say, OK, everything's OK. So we're just going to forward everything to the publishers. And this consistency check basically runs for all the samplers. OK, so when the publishers receive these Zs, they basically just, you get a list of 2t plus 1 Zs, potentially, if there was no complaint. And they literally just output the majority. And you do this for all the publishers. So they just output the majority of whatever they received for this specific set. And now it's pretty simple. So for each set S, we just set W sub S to P0 if there was a complaint. Otherwise, we just take the majorities of all the majorities that the publishers output. And in the end, we just XOR everything together. And I'm just going to give you a very rough idea of why this works. What are the key properties behind this? So first thing is that every set S of samplers has a strict honest majority. Second thing is if the set S did not receive a complaint, then all these honest roles in the set S, they agree on the same value, which basically means that you're committing to a value because there's an honest majority in this set. OK. And finally, there is a special set S star such that all samplers in this set are going to be honest. And this is important because the value that these guys agree on, this W sub S star, will be uniformly random and will also be hidden from the adversary at all times, which means that whatever the adversary does, whatever values he chooses to, for example, if he chooses to complain or he chooses to bias some value, these will all be independent of W sub S star. And so this XOR will be uniformly random. All right. And so this works. This gives you 5t plus 2, and we can save 2 roles with more care. All right. So this protocol, if you just specialize maybe for one corruption, this gives you like 7 roles. So it's kind of natural to think, whether we can improve on this, maybe naively. And I think it's instructive to just consider some very concrete settings. And let me just give you, a simple protocol to show that indeed we can do better. So here's the example for just one corruption. So again, same flavor. You have 2 samplers, 3 publishers, OK? And again, very simple. So first sampler just samples a bit, sends to everyone. Second sampler samples another random bit, sends to everyone. They all just publish whatever they got. You take the majorities of the reported values, and you just XOR them together. And why does this work? Well, this works because of case analysis. So if you have one corruption, say you corrupt one of the samplers, say role number 2, then what happens? You can, of course, lie and send different values to different publishers. But one thing that happens is that 2 of the publishers must receive the same value. It is important because this means you're essentially committing to this value that you're sending twice because you're going to take majorities. So then that part's fine. So if you try to corrupt one of the publishers, that's also fine because, again, 2 of the publishers will be honest and the samples will also be honest. So whatever you decide to do with the third publisher, they're not going to be a problem because you're anyway going to take majorities. Okay. So this works, and this gives you a protocol for 5 parties and 1 corruption. And you can generalize this combined with ideas from the previous slide to get this 5T roles instead of 5T plus 2. All right. Okay, so I should also maybe give you some ideas about our impossibility result, which is kind of subtle. So again, just a reminder, so we proved that basically if you want to do public randomness extraction in our model with, say, subconstant bias, then you need at least 4T plus 1 roles. So in other words, you cannot do better than, say, 1/4 corruption rate. All right. So just to clarify what we get in this case, so if you have this weaker adversary where we're considering in this talk, you get the optimal number of roles is somewhere between 4T plus 1 and 5T. If you consider our stronger adversary in the paper, you get something that's between 4T plus 1, 6T plus 1. Again, very interesting open problem to try to close this gap. And so let me just give you an idea of how this works. So just as a warm-up, let's just do 3 roles, 1 corruption. So showing that you need better than you cannot do better than, say, 1/3 corruption rate. And our idea, so here's a protocol structure. Again, parties roles broadcast public values. They send private messages to future roles, right? And the way this is going to work is that we're going to go party by party we're going to go role by role from last role to first role. And we're going to try to, have a strategy for corrupting the protocol. And we know that this strategy cannot work because we're assuming that the protocol exists and it works. And so this is going to give you some properties that the protocol must satisfy. And when we reach the first role, we're going to run into a problem. Okay, so let's look at, so we compute the coin in this way, and we look at the third role. So I claim that if there are 2 bits such that the last role can just choose essentially the output, the value of the coin, then that's a problem, right? Because if I corrupt the last role and this is true, I could say choose x3 0, and the value of the coin would always be 0. Okay, so clearly this is a problem. This biases the coin. And the conclusion is that whatever protocol we have, the first 2 public values must indeed fully determine the coin with high probability. All right, so then we can go to role number 2. And here, maybe one natural way to try to corrupt this is to maybe try to simulate in my head 2 honest runs of the protocol, and then try to choose the one I like the most. Okay, and I can do this because in green, I know that just the output, the public outputs of the 2 first roles would determine the final coin. All right, so I could sample x2 0 at x2 1 IID, like I would be honest, and then try to predict what they're going to say, right? What's going to be the final value of the coin, and just choose the path that I like the most. Again, this is problematic. There's some bias, and what we conclude is that if we have 2 independent honest samples, then they basically must lead to the same value all the time. So basically what this means is that just the first role actually determines the whole protocol or the value of the coin. And this is a problem, right? Because now you can corrupt just the first role. You just simulate 2 honest runs of the protocol. We know that the protocol is correct, so they're going to lead to 2 different values with high probability. And so role number 1 can actually bias the coin as well. And it is a problem. Okay, so I won't have time to go over like our actual result for 4 roles. So I'm just going to give you a very brief idea of why this doesn't work, why we need to be careful. And so again, this is our structure, right, of our protocol. Again, we start by corrupting, maybe we start by corrupting role number 4, and then everything is okay. Then we corrupt role number 3, everything is again okay. But then we try to corrupt role number 2. And the properties at high level that we're using is that 1, role number 2 must be able to influence the final output. And this is certainly true, and it's easy to show. But we also need that role number 2 must be able to predict which path leads to which value of the coin. And this is actually the hard part. And this is hard because role number 2 doesn't know the private message from role number 1 to role number 3. And so we kind of need to find a way to get around this. And it is subtle. But I'll leave it at that, and I'll leave you to check the paper. So yeah, just wrapping up very clearly. So we looked at YOZO, which is stateless NPC because of denial of service attacks. We consider public coin tossing with worst case corruptions. Why? Because we want something that's still secure if the role selection mechanism is biased. We want to go beyond round-based MPC techniques, and we get some positive results. So we get protocols for 60+1 or 5T roles for T corruptions, and just leaving you here with some open problems. So of course, it'd be very interesting to close the gap between our two results, positive and negative. Also, I'm not sure if you know this, but our protocols are super inefficient. They have exponential complexity in the number of roles. And it's a very interesting open problem to just try to get polynomial complexity in number of roles. And finally, just try to get more functionalities, because we just did coin tossing. So yeah, thanks a lot. And
thanks for the talk. We have time for one short question while the next speaker sets up. If you have questions, please go to the microphones here, so there's people on Zoom hear you, or you can also ask questions in the Zoom chat. So if there's none, maybe I can ask you, what is the conjecture? 4 or 5? Where is the right?
Probably, yeah, I think 4T+1 is probably tight.
The next speaker here also?
Yeah. Oh. Yeah, 4T+1 is probably tight. Yeah.
Okay.
Yeah, I think so.
Okay, thanks.
Thanks.
So our next talk is on non-deterministic hardness versus non-malleability by Marshall Bolt, Anna Dachmann-Solet, and Julian Loss. And Julian is giving the talk.
I don't think the slide is being shared. That's good here. Okay. Hi, my name is Julian, and I'm going to be talking about non-deterministic hardness versus non-malleability. This is joint work with Marshall Ball from NYU and Dana Dachmann-Solet from UMD. Okay, so suppose that we're in the following setting. We have a party A and a party B, and A, Alice, would like to send a message to Bob on the right side here. So what she does is she encodes this message as a series of bit strings, and then she sends this message to Bob. But the problem might be that M now could contain errors, because there could be an adversary, say, on this channel that flips a couple of these bits, and then Bob doesn't get the correct message. So one simple solution to this problem might be to apply an error correcting code. So an error correcting code is a code which contains an encoding function. And you can apply this code to the message M, and you get as an output code word, which Bob can then decrypt to the original message, even if there were some errors and the code word was flipped into a different code word, C hat. But now the problem is that we can't actually guarantee that the decoding will output the original message. And the question is, what can we still guarantee in this question, in this setting? So a little bit more in detail, we refer to this kind of attack where some bits of the code words are flipped as a tampering attack. So an adversary here tampers the original code word C into a tampered code word C hat, such that the decoding of C hat does not yield the original message M. And this can have very, very bad consequences, as you can imagine. So here's a simple example. Maybe Alice is sending or trying to send Bob a message M, order pizza for dinner, and now there's an adversary here. and he's tampering with this message. And so what you end up with is a message that says, order pineapple pizza for dinner. And this is, of course, something we really want to avoid. And as you do. And you could apply a MAC here, but you know, a MAC is a keyed primitive, and it's an interesting question of whether you can actually do this without having any keys. And this is the kind of question that we're trying to answer here. And the tool, well, I'm sorry, this is blocked, but the tool that we're trying to apply to get here is a tool called Non-Malleable Codes, introduced by Jimbowski, Piotczak, and Vix in 2010. So a non-malleable code is just a code with an encoding function E, a decoding function D, with roughly a property that prevents tampering as follows, or in the following sense. So if you input M to the encoding E, and then E outputs a code word, and now the adversary tampers with this code word, then the decoding function is guaranteed to either output the original message or to output something that's completely unrelated to the original message. Okay, so this in some sense captures the intuition that the best attack that the adversary should be able to do is to delete the code word from the channel entirely and replace it with something that's a completely unrelated code word. So defining security is a little bit tricky in this setting, so let me try to do it here. So we're going to use the real world, ideal world paradigm to define the security experiment here. So I'm going to show you the real world experiment first. So this is just a tampering experiment. I'm emphasizing here that the encoding that we want to reason about here is actually randomized. So I'm going to input the message to the encoding, then the encoding will output a code word. And then we're going to model the tampering function now as an efficiently computable function f, which takes in the code word, it outputs a tampered code word c hat, and then c hat is fed into the decoding, and then the decoding outputs, well, whatever comes out of D. So this is the real world experiment. And now for the ideal world experiment, we're going to use a simulator, which actually doesn't take the message M as an input. So what the simulator does is it's going to either sample a constant word same or something that comes from the input-output space of this code. And this simulator now induces basically a distribution which should be indistinguishable from the distribution induced by the real world experiment as follows. So if we input M here to the experiment, or the experiment is defined relative to M rather, then if the simulator outputs same, M will be the output of this distribution, and otherwise, if it's M hat, it will be M hat. Okay, and so as I said, this induces a distribution df that depends on the tampering function, and it is a distribution over identity / constant functions over the input-output space of this code. And what we want is that this distribution is statistically indistinguishable from the real-world distribution. And if a code has this property, then we call it a non-malleable code. Okay, so now that you've seen the security definition, here are the goals of this work. Basically, what we're looking for here are efficient and explicit non-malleable codes. We want constructions in the plain model and from plausible assumptions. And finally, we are interested in, as broad of a tampering class as we possibly can get. Ideally, we would like a tampering class that includes all arbitrary polynomial size circuits. But unfortunately, this is not possible. So these goals are inherently conflicting. And the reason for this is because there is a very simple attack, which I can just show you here. So basically, the attack works as follows. Suppose that I'm encoding M, I get C. And now I can actually write down an efficient tampering function here, which is just the following. So it first decodes the code word, then you get M, you add 1 to this message, then you re-encode it, you get C hat, and then C hat will be a code word basically that violates this property of non-tamperability of the non-malleable code. So the reason that this is efficient is, of course, because the code itself is efficient. And so we can't hope to get security against an arbitrary polynomial size tampering class if we would like the code itself to be efficient. So what is the next best thing that we can hope to get? Well, this is what we actually are going to try to do. So for every constant C, we will give an efficient non-malleable code against n to the c-sized circuits or n to the c-sized circuit tampering classes. And the problem that we have to somehow overcome is that this is actually known to imply polynomial circuit lower bounds, which are, of course, notoriously hard to derive. And to not have to do that, what we're going to do is we're going to assume these circuit lower bounds and then reduce to one of them. So that's the roadmap. And before I go into our proof techniques any further, let's actually have a brief look at some prior works and their limitations. So there is one line of works, which is in the CRS model. And basically, these are non-explicit Monte Carlo constructions. There is the Cherchi-Goswami construction from 2014 here. It's in the CRS model, and also the construction of Faust, Mukherjee, Venturi, and Vix, also from 2014. So as I said, both of these constructions are in the CRS model. We would like to get a construction in the plane model. And there's also a line of work on computationally secure constructions from relatively strong crypto. So what do I mean by strong crypto here? So this is cryptography that potentially has some instantiation in the plane model, but currently requires the random oracle model. So in some sense, these constructions also are not explicit. So here we have works of Ball, Dachmann, Solet, Kulkarni, Lin, and Malkin, 2019, and also the works of Dachmann, Solet, Komagotsky, and Pass from 2020. Okay, so now that we've seen some prior work, let's actually have a look at the main hardness assumption that we are using and the theorem that we would like to prove. So to state the hardness assumption, let's actually define E as the class of all languages that are decidable within deterministic or exponential deterministic time. And the conjecture that we're going to use here says the following. So we're going to require the existence of a constant gamma between 0 and 1, and some language in this class of languages E, such that for almost all n, L should be undecidable for non-deterministic circuits of size 2 to the gamma times n. So some properties of this conjecture are that it's a worst case assumption. It's actually, in some sense, doubly worst case. It's very robust because we only require the existence of such a gamma and the existence of such a language. So that makes it a very, very robust assumption. It's been used sometimes before in the literature also. It also has the nice property of having some complete problems, which is very useful to prove reductions. And finally, it's, to the best of our knowledge, orthogonal to cryptography because it's not known to imply the existence of one-way functions. Okay, so now here is our theorem. Suppose that this conjecture is true, then for all constant C, we show that there exists an explicit non-malleable code for n to the c-sized circuits. Now, I should say that our non-malleable codes actually have a slight correctness error, which is n to the minus c. And an open question is if we can actually get something that is statistically or even perfectly correct. Okay, so the key obstacle that we have to overcome in our proof is that on the one hand, the code ED has to be hard for n to the c-sized circuits. But on the other hand, our reduction from conjecture 1 has to simulate the tampering experiment, and these goals seem to conflict with each other. So our solution is to actually have a non-deterministic reduction and to use a strong statistical tool, which I'll introduce on the next slide. So the strong statistical tool that we're starting from is a class of non-malleable codes against something known as bounded communication tampering. And actually, it's not only bounded communication, but it's actually split state tampering. So this is going to look as follows. In the tampering experiment, the code will now produce a left and the right code word. It will give the left code word to Alice and the right code word to Bob. And now they're allowed to talk to each other, but the transcript of their communication has to be much smaller than either of these code words. And in the end, they're going to output their respective tampered half of their code words. And the nice thing about this class of tampering attacks is that we actually know explicit NMCs for these tampering classes in the standard model. And this is where we sort of start from. Okay, so here is our construction a little bit more concretely for n to the c size circuits. So we start from a non-malleable code against the class of tampering attacks that I just showed you. So let's denote this code as E tilde D tilde. And we also start from a very special PRG. This is actually the reason that we required this, this conjecture, that's where we really needed to instantiate this PRG. So this is from prior work, of course. But this PRG is a special PRG that has the property of being uniform with respect to deterministic circuits, non-deterministic circuits of size n to the c. So I should point out here that this, of course, means that the PRG is actually not evaluatable for non-deterministic circuits of this size, because if you can evaluate it, then of course you can distinguish it from random. So you actually need a larger circuit size to even evaluate this PRG. So keep that in mind for the next couple of slides. So now here's our code. So on input X, it's going to output a seed and a right half of the code word CB, such that CB corresponds to the right half of the code word of applying E tilde to the input X. And the PRG, the PRG evaluated on S corresponds to the left half of a code word if we input it to this encoding E tilde. And in our work, we actually show an efficient way of doing this. Okay, so now the decoding, of course, follows quite straightforwardly. You just apply the PRG to the left half of the code word, and then you apply the original E tilde decoding function. So this is our construction very roughly. And the proof idea now, I mean, I cannot go into details here, but I'm just going to sketch a couple of the very, very high level ideas for you. So the proof idea is to basically turn an attack on our code into a distinguisher against this underlying PRG. And here is how this is going to work. So we know that if the code word is generated according to the underlying split state non-malleable code, then this is secure because we have a construction for that. But if now we de-randomize this code by generating the left half of this code word as applying the PRG to the seed, then actually there is an efficient tampering attack. And this attack uses the fact that Alice in this experiment can send over the seed, which is short, so she doesn't exceed her bound on the communication here. And now Bob can apply his efficient tampering function F locally on S and his half of the code word and send back an also short seed S tilde, which is tampered. And now Alice can evaluate the PRG locally, and both of them can output their respective halves of their tampered code words. Now, intuitively, this should lead to a distinguisher on the PRG, because these two worlds are not the same. In one world, we have a secure non-malleable code, whereas in the other world, it's completely broken. So somehow this should lead to a distinguishing attack on the PRG. And this is exactly actually what we do. And I'm going to show this in the next step. So I should point out a couple of things, though, first. First of all, Alice is computationally much more expensive than Bob, because she has to evaluate this expensive PRG on her side. Whereas Bob is very efficient because all that he has to do is evaluate the tampering function. Okay, and so this leads us to consider actually a class of protocols called Merlin-Arthur protocols, where on the left side, we have a wizard called Merlin, and he's going to act as the prover in this protocol, and he has unbounded communication power. On the right side, we have Arthur, who is supposed to be efficient because he's only human. And roughly speaking, Alice from my previous slide and Bob from my previous slide are going to correspond to these two entities in this slide here. Okay, so Bob was efficient, so Arthur is efficient. Alice was a little bit inefficient, but that's okay because now she's going to be Merlin in this protocol. Okay, so roughly speaking, the protocol that we build is supposed to accept tuples of the form S, comma PRG evaluated on S, and it's supposed to reject tuples of the form S and a uniform string. So we don't get perfect correctness or soundness here, but that's actually okay. We don't need that. And as I said, Merlin is unbounded, so it can easily evaluate the PRG, whereas Arthur is efficient because it only has to evaluate F. Now, finally, once we have this protocol, we can actually turn this into a non-deterministic distinguisher for the PRG via known techniques. And yeah, that's the proof sketch for our main results. If you're interested, then please have a look at our paper. And that concludes my talk. Thanks.
Thanks for this great talk. We have time for 1 or 2 questions. I don't see questions on Zoom. So we have a short question. So your decoder also needs N to the C space, right? So is there any chance of maybe using Prfs instead PRGs to?
That's a good question. So sorry, what's the question actually? So
is there any chance to use Prfs instead PRGs?
I see. So, that's no, but maybe you can use PRG from a little bit of a weaker complexity assumption, because you could maybe use a space, some kind of space constraint. So that might be possible. But I don't know. I'm not.
Okay, if there's no more questions, then maybe the third speaker can come up.
Okay. Oh, yeah. Oh, yes.
So our third talk is on short leakage resilient and non-malleable secret sharing schemes by Nishant Chandra, Bhavana Kanukurti, and Lailakshmi Bhavana Obatu. And Shruti is giving the talk.
Thank you. Thank you for the introduction. So today I'm going to be telling you about how we end up building short leakage resilient and non-malleable secret sharing schemes. So this is joint work with my wonderful co-authors Nishant Chandran, Bhavana Kanukurti, and Sai Lakshmi Bhavana Bhattu. Let's start by looking at secret sharing schemes, which we all know about and love. This was introduced in 1979 by Shamir and Blakely. So the goal of this protocol, just to recall, is there's a dealer, Bob, who has some secret and doesn't want to keep the secret in its entirety. Instead wants to split it into amongst n parties into these shares, S1 through Sn. And the kind of property that you seek from these are that if you take T amongst these n parties and use their shares, it would be enough for you to reconstruct and recover the secret. So this is basic correctness. And T here is some threshold basically that you can set, and it's less than equal to n. And on the other end, you want a privacy guarantee that if less than T parties are corrupted by some adversary and he procures those shares, you don't want anything to be leaked about the secret. So how do we capture this a bit more formally? We do that by saying that whether you pick a secret S or a secret S prime and consider a set of less than T shares corresponding to S, that looks indistinguishable or close enough to the corresponding set of shares for S prime. So throughout our talk, we'll be in the information theoretic setting, which means the closeness that I'll be talking about would be statistical distance. So about 2 decades post the introduction, came about this class of attacks that have been looked at widely called leakage attacks. It was introduced by Kosher, and in the context of secret sharing, this particularly led to a natural question. What if, in addition to the T-1 shares that the adversary procures, he's also allowed to get some bounded bits of leakage from the remaining shares? And turns out this is not something that directly gives security in the standard secret sharing schemes. So in fact, a bit more formally, the Shamir secret sharing scheme that we all use widely in several applications breaks, in fact, if you give even 1 bit of leakage on the rest of the shares, in addition to the T-1 full shares. So this was shown by Guruswamy and Wouters in 2016. And naturally, this is what led to a formal study of leakage resilient secret sharing schemes. And basically, in addition to the standard correctness, now instead of just seeking privacy, we want something stronger, which we call leakage resilience. So recall the privacy only guarantee that if you give T-1 shares, there should be nothing leaked. Now instead, we want to capture something that can be given about all the shares. So particularly, if I have to generally capture it, I'll pick some function family that captures my leakage and the privacy as well, potentially. We'll get to the specific function family. But for this function family, whenever I pick a function and apply it on all of the shares together and output it, this F applied on the shares, which is my leakage now, it captures essentially the leakage, that should give no information about the secret. So as before, this was captured by saying for any two distinct secrets S prime, the F applied on shares of S looks close enough to F applied on the shares of S prime. So what is the kind of family that are natural in the setup? Something that also captures privacy, that we'll get to in the next slide. So more generally, what are the parameters of interest? As with regular secret sharing schemes, the first crucial parameter of interest is share size, right? So for regular Shami secret sharing scheme, we know we have the optimal share size, which is the message length. Particularly, it measures essentially the size of the largest share amongst all the n shares. And in the leakage resilient setup, the best share size one can hope for is actually the message length plus mu, where mu is the bounded number of bits of leakage that you can give per share, essentially. So this is the best you can hope for in the leakage resilient setup. And second is the leakage family, which I promised to mention about. So the particular family of interest which we'll be looking at today is called the local leakage family, which was one of the first studied ones. And here, essentially, if I look at it from the perspective of an adversary challenger game, the adversary sends this function, which now comprises of n separate functions, n being the number of shares that you would have. And the way the leakage works in this family is basically each fi acts on only one share, which is the si. So S1 through Sn are the shares corresponding to S. And you return basically fi of si as the share. So note here, the adversary sends all these functions in a single shot. So it's a non-adaptive way of sending the leakage functions. And each function acts on a single share. So it's kind of independent leakage on each share. So particularly, this captures privacy because T-1 of these functions can essentially be the identity functions. So they will just give out the full shares. And the remaining functions would be giving out some mu bounded bits from the share that it takes as input. So this is basically the local leakage family that would be of concern for our talk today. But in literature, people have studied stronger leakage families thereafter as well. So that brings me to prior works. What is known in this realm? There has been a long line of research since the introduction of these schemes. And broadly, most of these works, as I mentioned, focus on strengthening the leakage model because it is truly an important aspect to get the strongest possible leakage model in the setup. So they've studied adaptive and joint versions of what I just presented to you. However, for all these schemes, the share size of the leakage resilient secret sharing is omega of message length. So particularly, they have polynomial blow up or like it's really large share size. So our focus is to first start and look at the local leakage model and see what is known about the trade-off between the share size and leakage in the known schemes. So broadly, in this local leakage model, there are two lines of work. The first, which look at the Shamir secret sharing scheme in itself, because it's widely in use. So the natural question to ask is, does Shamir secret sharing scheme in itself satisfy some form of leakage resilience to begin with, in some setup at least? And turns out it does. So in this work, basically, what is shown is for a restricted setup where you consider a large characteristic field, a large number of parties, and also you restrict the full share corruptions to be only a constant number. So only constant number of full shares are given. Under these restrictions, there are two trade-offs you can get. So if you restrict the threshold to be at least n minus O of log n, N is the number of parties recall. Then the Shami secret sharing allows you to leak 1/4 of the bits from each of the share. So we are in the local leakage model. Each leakage is from a share independently. So this will allow you to leak 1/4 of the bits from each of those shares. On the other hand, if I want the threshold to be alpha n for some alpha, there, however, you will only be able to leak constant number of bits per share. So this is the kind of trade-off that you have from Shami secret sharing scheme in this restricted setup. Is this the best you can do? In some sense, it is shown to be the best you can do with Shami secret sharing scheme. So this is what led to the question, can we get like the optimal trade-off between the leakage and the share size? And that led to the other line of constructions in this realm, which was building generic compilers that take in any secret sharing scheme and convert it into a leakage resilient secret sharing that works for this leakage model. So this was particularly for the local leakage model, these two works build a generic compiler. And amongst these, the work of SV19 show best trade-off known for the setup. So particularly for any arbitrary number of parties and threshold that you can consider, what they show is the share size that you can get is 3 times the message length plus mu. So there's a factor of 3 blow up. And however, you can get any, like, so the mu bits of leakage that you get per share, that can go for any arbitrarily close to 1 minus over 1 times the message length. So this is basically, in some sense, the best leakage you can hope for, but the share size is blown up by a factor of 3. So the known lower bounds for what is the trade-off between share size and leakage doesn't apply to the generic compilers. And hence, the scope for getting really the truest optimal trade-off between the share size and leakage is open somewhat only in the generic compiler context. And so we'll be looking at that. And the particular question we ask in this work is, can we actually get a leakage resilient secret sharing scheme that matches what we know is the best and gives an efficient scheme? So can we get the optimal share size and leakage trade-off, particularly in the local leakage model at least? So that is the focus of our results. So a bit more formally, our results are the following. So the first result that we get is basically we build the a leakage resilient secret sharing scheme for this local leakage model in threshold access structures that allow mu bits of leakage per share, and we get the optimal share size of message length plus mu, as I promised. And further, we can also extend our compiler to work for general access structures. So it will be a rate preserving compiler for general access structures. And as an application, we also show how we can use the original connection known from Goel Komar's work and actually get a non-malleable secret sharing scheme with the share size, much improved share size of 4 times the message length. In addition, we introduce a variant of non-malleable secret sharing that just works for random secrets. For that, we show that you can even get a further improvement in share size to 2 times message length. So this part I'll not be talking about. The focus of our talk from here on would be on just getting, showing you how the construction for the threshold access structure works. Okay, so let's start by looking at the building blocks that we need for our construction. We need only one single building block, which is linear extractors. So what are linear extractors? First, randomness extractors were introduced by Nissan and Zuckerman in 1996. And the version of them that we'll be looking at are seeded extractors. So particularly, the extractor function takes in some source string that's drawn from this distribution W, which is known to have a high min entropy, given some extra information. So Z is some string that's given about W. In spite of giving that, you know the min entropy of W is high. And in addition, the extractor takes as an aid a random string called seed. It's a short random string. And with that help, it is able to produce a string Y, which looks close to uniform. So a little bit more formally, the uniformity guarantee here is that the extractor output looks close to uniform, even when I give out this additional information Z about the source, and you give out the seed also out and clear. So this is the uniformity guarantee that we need. And in addition, we need a linearity property, which essentially says that for a fixed seed S, the function extractor on the fixed seed S. So it's now just a function of the source. And this function is a linear function. So particularly, we need such a linearity for its invertibility. And in the next slide, I'll get to what kind of invertibility we need. But that's why we use linear extractors. And in literature, we know linear extractor with great parameters in terms of the known seed length and everything. And I'll get to that also when we talk about the share size. Okay, so what is the kind of inversion we need from the linear extractors? So particularly, if I consider the source distribution to be just the uniform distribution, which is enough for our construction. What I want is for such a linear extractor, there should exist some efficient invert function, which I called invert extractor. And it satisfies essentially, firstly, a basic property, which just tells you that this invert function can, in some sense, get a correct source string when I invert it on the correct extractor output. So if you notice, it takes in as input the extractor output and the seed, and it spits out something which technically should give you the correct source string that led to the extractor output. So what this is saying is that when the invert extractor is applied on the correct extractor output and the seed, that distribution would look essentially identical to uniform, which was my original source distribution. So this is the kind of first property you want from the invert extractor. Besides that is the like standard correctness feature in the sense that whenever you have a guarantee that for the fixed seed and the string y, the relation is corresponding to some valid extractor output, which means that there was some source to begin with for which the extractor output gave y. If this is the relation, then I will always be able to invert correctly. So basically, it means that this function would output some w prime such that the extractor on w prime and s is y with probability 1. So whenever I give a correct string drawn from the extractor output space, you will always be able to invert. That's all this is saying. But if not, I would output some special symbol, which is bot. So if there is no such w that you can invert to, you'll output bot essentially. Okay, so this is the kind of inversion feature that we need from it, and we'll see where we exactly use it. So with that, I'm ready to tell you how our construction works. And it's a fairly straightforward construction to think about. Basically, you take the secret message M, and the first thing, as I said, is we build a compiler. So we first share it using a regular secret sharing scheme. So particularly, we are in the threshold setup, and we care for optimal share size. So we'll share it using the Shamir secret sharing scheme, which gives you the optimal share size, at least in the standard secret sharing notion, right? So we'll share it using the Shamir secret sharing scheme. Now I pick a seed for the extractor. And what I do is I invert each mi using the invert function for the same seed s. So note here, like I'm using the same seed for each of the invert function, and I'm taking this mi to represent my extractor output in some sense. So I'm inverting and recovering some source corresponding to this output. And then I just secret share my seed using Shamir secret sharing scheme with same threshold T, and I output the shares S1 through Sn. So the final shares here are just each, so the share I is just WISI. Okay, so of course, what I did not mention about here is the scenario where the invert outputted bot. What if there was no valid WI? That's a possibility here. In such a case, I'll just ensure correctness. And for that, I will just give you the original message, MI. If there's no WI, if there's even one J for which the WI did not exist, I will end up giving you MIs for all the shares. So clearly here, you will not achieve leakage resilience, but what we'll end up showing in the proof is that this only occurs with negligible probability. So it doesn't spoil the leakage resilience. Okay, so first check correctness holds. Well, in the first case, it directly holds because we had WIs and SIs. You could reconstruct the SIs and get the seed first. Then you could just apply the extractor and recover the TMIs from which you could reconstruct the message. So that was a case where you had the WIs and SIs, and here you already have the MIs to begin with, in which case you can just reconstruct using the Shamir secret sharing. Okay, so why does leakage resilience hold? And I'd be able to take you through a high-level sketch of why it holds. So let's start with the first case. As I mentioned, here you want to show that this is a case where you can't hope for leakage resilience, right? But what we'll end up showing is that the probability that this there exists some Wj for which the invert extractor output spot, that would be actually negligible. So this case in itself happens only with negligible probability. Why is that? This uses an added feature that Shamir secret sharing scheme already has, and we assume this, which we call local uniformity. So what does it say? That if you look at any individual share of Shamir, that itself looks uniform. So each mi, the distribution on one particular share, that looks close to uniform. And this is something you can see that Shamir scheme already satisfied. Once you have this, you can use the extractor security and take this to the case that the mi actually ends up looking close to the extractor output. So what does this tell me? Like whatever you're feeding in as the input to the invert extractor, you can ensure that at least it's close enough to being picked from the extractor distribution. And we know that when that happens, so the correctness is guaranteed. You will be able to output a wi with probability 1 when that happens. So except for the error that is there by this closeness, you're good in this situation. So only with the negligible probability, there will be a bot situation. So this case does not occur with high probability. Hence, we can look at the main scenario. What happens when WISI is output, right? So here, for the leakage resilience, recall we are in the local leakage model, right? So it was all individual FIs acting on each of the share. So particularly the last T-1 shares are full shares, and the remaining are all, like, for the sake of this proof, like consider the last T-1 shares are full. And the remaining are the ones which output bounded bits from the share. So how does leakage resilience work? First, look at the ones that correspond to the leakage part, right? The N-T-1 shares for which you outputted bounded bits. The point to note here is because of the property of the extractor, you had the guarantee that the invert extractor, whatever it outputs, that distribution is close to uniform. So what you can actually capture here, that the leakages that you get from each of these WISIs turn out to be independent of MI, because you can show that the WIs here look close to uniform. So the point here is you want to ensure that this N-T-1 shares corresponding to leakage, they end up using no information or giving no information about the MIs in itself. Because for the next part, which is the full share, I want to use the privacy of the underlying scheme. So what I mean is, once you've used and shown that the leakage part corresponding to the first set of shares, they are independent of the MIs. Now for the full shares, I can just use the underlying privacy of Shamir and guarantee that it's okay to give these full shares. So they will be independent of them, essentially. So that's essentially the high-level idea behind how we show leakage resilience for this. So just to conclude, what I showed you here today was a construction for how to get these leakage resilience secret sharing schemes for the threshold access structure in the local leakage model that gets the optimal share size and leakage as well. And our compiler also, and what I did not talk about is that our compiler also extends, and we can prove a rate preserving version for the general access structures. And in addition, we also have applications to non-malleable secret sharing schemes with improved share size. So if you're interested, you're welcome to take a look at our paper. What is open here and still interesting to look at is what about the stronger leakage models? So for the adaptive joint model, there's only one construction known that has a constant rate, and even there, the constant is quite big. So of course, achieving optimal share size for a stronger leakage model is a very interesting open problem to look at. Thank you for listening. Yeah.
Okay, thank you for this great talk. So while the next speaker sets up, maybe if there are questions, please come forward. So our fourth and last talk in this session is called Cryptography from Pseudo-Random States by Prabhachan Anat, Luo Wenquan, and Henry Yuan, and Yuan is giving the talk.
Should I start? Should I start now? Should I start now?
Yes.
Oh, okay. Yeah, thank you for the introduction. So now for the last talk of the session, I'm going to talk about a very different kind of randomness. So I will be talking about this work about constructing quantum cryptography from pseudo-random quantum states. And this is joint work with Prabhachan Anand from UCSB and Henry Yuan from Columbia. So let me start by maybe giving you the takeaway if you are not a quantum person. So let's start with the following question. Let's say, take your favorite cryptography, AES, SHA-3, RSA, or assumptions like lattices, or even concrete cryptographic protocols like TLS. Can you actually prove the security of any of these protocols? And thanks to decades of cryptographic research, we know that this is probably not possible because any unconditional security proof of any of these protocols will imply the existence of a primitive called one-way functions. And as you might have heard in Julian's talk, this thing is considered to be the backbone for cryptography. And furthermore, you will also settle the P versus NP question and win $1 million. So this is probably not possible without assuming any assumptions. So the focus of the talk today is going to be on quantum cryptography, which is a cryptographic protocol for quantum parties, meaning that even honest parties participating in the protocol have quantum capabilities. And so prior to our work, all non-quantum cryptography are either information theoretic or they are computationally secure, but they assume at least some assumption that is that would imply one-way functions. So the contribution of our work is showing that for a broad class of quantum cryptography, it is actually not necessary to assume the existence of any kinds of one-way functions. And so you can also think of this as the evidence that maybe there are no barriers, at least the similar barrier for classical cryptography for getting a security proof. So this follows by the work that I'm going to talk about today and a prior work by Krashmer last year. And there is also a concurrent work by Morime and Yamakawa who show something similar in spirit, but with different proofs and different techniques, which is going to be happening just right after this talk in the other room. Okay, so now let's delve into the more technical specifics. So the focus of today's work is going to be this quantum object or primitive called pseudo-random quantum states, or PRS for short. So this object was introduced 3 years ago by Ji, Liu, and Song. So informally, this object is like a pseudo-random generator in the sense that it also takes as input a short seed. However, unlike a pseudo-random generator, the output is a quantum state instead of a pseudo-random bit string. And the pseudo-randomness property that you are supposed to require on this object is that this thing should look pseudo-random in some appropriate quantum random notion called Hardness. So let me now introduce you to this Hardness definition. So just to remind everyone, for a quantum state, let's think of a quantum state for a single bit, also called as a qubit, which is formally just a unit vector in two-dimensional complex Euclidean space. And for n qubits, it's just n tensor products of qubits. So it's a 2 to the n dimensional complex Hilbert space. And the hard random state is basically the uniform distribution over all the unit vectors lying on the unit sphere of this 2 to the n dimensional space. So one immediate observation that you can make is that even to describe an approximation of the hard random state, you would need an exponential number of bits. And because we define this hard randomness to be a uniform distribution over the sphere, it also satisfies a crucial property that we'll use later called unitary invariance, which roughly means that for any unitary, which you can think of as a rotation of the sphere, the hard random distribution after applied unitary is still the same distribution as the original distribution. Okay, so now let me give you the definition of PRS more formally. So we call a quantum algorithm G to be an n-qubit PRS generator if it satisfies the two criteria. The first criteria says the generation is efficient, so it takes as input a lambda bit seed and runs in some polynomial time, and then outputs a pure state of n qubits. And the pseudo-randomness says that these outputs, even with many copies, looks just like many copies of hard random states. So formally, we are saying that if for any polynomial number of copies t, t copies of a random PRS state is computationally indistinguishable to a hard random n-qubit quantum state, also given t copies. So just some observations on this definition. First, unlike PRG, here we need to give many copies because quantum states, hard random states in particular, are not clonable. So the more copies you get, you can actually get more information. And the second observation is that the security is supposed to hold just like for PRF for any arbitrarily large number of copies as long as it's polynomial. And if this is a fixed number, then this has already been studied in prior works. It's called a T design. If T is bounded, here we are considering T to be not unbounded. Okay, so here's what we know about comparison between one-way functions or equivalently pseudo-random generators versus pseudo-random states. So in the original work that introduced this object, they show that if you start with one-way functions, you can construct pseudo-random states for any output length that's super logarithmic. And once you have that, they show an application of such an object. In particular, they give a construction of private key query secure quantum money, which is a fancy quantum crypto. On the other hand, we don't know whether pseudo-random states implies one-way function or even something more wild like or more like weaker like P not equal QMA. And if you look at what would go wrong with the classical proof that maybe PRG implies P not equal NP, here the problem is basically that when you are trying to do that reduction, you get a quantum statement. However, for P or QMA, even for QMA, the statement is classical, although the witness is quantum. And indeed, there is this work by Krushmer last year showing that there is an oracle relative to which P equals QMA, and yet pseudo-random states exist. So from a cryptographer's view, this is a black box separation between pseudo-random states and one-way function. In particular, it tells you that you cannot construct a one-way function, post-quantum or not, from a pseudo-random state in a black box way. Okay, and so all of this points to a belief that maybe pseudo-random states by themselves could be a weaker quantum hardness assumption than one-way functions. So the starting point of our work is to ask the following question. So forget quantum money, which is way too fancy. What kind of task that we already consider in the classical literature can we achieve just with just assuming the existence of PRS. And then we run into a bunch of difficulties of using PRS. So let me quickly mention them. So this is also observed in the original work by JOS, which just says that for a hard random state, or more or less equivalently PRS, the pseudo-random state output is highly entangled. And this is an issue because an entangled state is kind of brittle in the following sense. So for a concrete problem, to the best of my knowledge, we still don't know how to prove something like this, which is assuming you have an n-qubit PRS. Can you construct an n prime qubit PRS for any non-trivial n prime? For example, starting with a PRS whose output is 4 times longer than the seed, can you construct another PRS that's only 2 times longer? And of course, for PRG, this is trivial. You just truncate the second half. However, this doesn't work for PRS because if you truncate the second half, you will now get a mixed state because they were entangled. And once it's mixed, then it's no longer indistinguishable from hard random because the hard random state is a pure state. And furthermore, for PRS, even if the output length is not expanding, this object could still be non-trivial. In fact, the oracle separation considered by Kretschmer has the output length exactly as long as the input C length. So, well, at the end of the day, we came out with this new object called, which is a state analog of PRF, which we call Prfs, which I'll define shortly, that allows us to get around these issues. So our result basically is summarized as follows. So using this object I'll define shortly called Prfs as an important intermediate construction, we showed the following construction of useful cryptography from pseudo-random states. So the first construction is that if the PRS output is super logarithmic long, then we can do one-time encryption of any message length. And secondly, assuming the PRS output is a little bit more than 2 log lambda, we can actually construct statistically binding commitments. And furthermore, we also show how this quantum commitment that we construct is compatible with known literature constructing secure multi-party computation protocols from one-way functions. And as a corollary, we get secure multi-party computations just assuming pseudo-random states. So let me remark that these parameters are somewhat optimal in the asymptotic sense. So in particular, this work by Brakersky and Shmuley show that if the output length is logarithmic for some constant, then you can actually construct statistically secure PRS. And for all we know, all of these objects like one-time encryption and commitments are not possible information theoretically. So so we do have to assume the output length is at least some logarithmic. However, there is still some gap, which is basically saying that there are some constant times log. So if your output length is that, then we don't know whether it gives you crypto, nor do we know how to construct it statistically. So the concurrent work, which is happening after our talk, considers a somewhat different PRS. So they also show how to construct commitments and also one-time signature, but they assume the output length is expanding. But on the flip side, they only require the PRS to be secure when you're only given a single copy, whereas here we are assume many copies depending on the output length. Okay, so I promised you I will talk about this object, so here it is. So this PRFS is called pseudo-random function-like states. which, as I said, is a pseudo-random function analog to pseudo-random state. So we say, so I will just highlight the difference between a PRFS and PRS. So basically, for a PRFS, allows you to, so for the generator algorithm, it additionally allows you to give it a short input X. And the pseudo-random, you can think of this input in the same way as an input to a pseudo-random function. And the pseudo-randomness requirement says that, again, for any number of copies, but also for any number of indices that you want to query to this PRFS, the output states looks just like a bunch of independent Hard-random states drawn from the Hard-random distribution. And we remark that if we can have this PRFS object, then a lot of non-classical crypto that you build using PRF can also be built, readily built by replacing the PRF with PRFS. So this includes like secret key encryptions, message authentication codes, and so on and so forth. Okay, so I believe most of you might have a natural question to ask me, which is, okay, but what about candidate construction of pseudo-random state? And is this where I will finally talk about wormholes? So stay tuned until the end of the talk once I finish telling you how we construct this crypto. Okay, so first let me tell you how we construct pseudo-random function-like states from PRF. So it turns out this is the crucial observation that we made that made this construction work. So let's say you're given a quantum state of n qubits. Well, one thing you can do is to take the first qubit of this state and then measure it. Then once you measure it, it will give you one of two outcomes, either 0 or 1, just like a classical bit. And the remaining state, which is now n-1 qubits long because you measure 1 qubit, is going to collapse some post-measurement state. If you measure 0, and similarly, if you measure 1, you will also get another post-measurement state. And it turns out that we can show that if your starting state is Hard-random, so it's drawn from the Hard-random distribution, then these two post-measurement states are actually close to independent copies of Hard-random states by themselves, although they are shorter by 1 qubit. So this is a very powerful observation, because once we have this, we can just replace the Hard-random state with a PRS state. And we can say, well, now I've generated 2 PRS from 1 PRS. And furthermore, you can extend this construction to measuring multiple qubits, not just 1 qubit. So, so here's how we construct PRFS from PRS. So basically, you just take the first d qubits. It doesn't matter how you label these qubits, but you just take any d qubits and then measure them. And then condition on getting x, which is your input, you just output the post measurement state on the remaining qubits, which is there are n-d of them. And we show that for Hard-random distribution, this post-selection success probability, or like this conditioning, this event that we're conditioning on, this probability is exponentially concentrated around 1/2 to the d, which means that if we can just do rejection sampling to produce these states, given that d is only logarithmic long. Okay, so the formal theorem that we show is that if you have a d plus n qubit pseudo-random state, then you can construct an n qubit PRFS with d bits input as long as this d is only logarithmic. Okay, so now let me tell you about how to construct encryptions. So the task of encryption is that two parties share some secret that is n bit long. And then let's say Alice wants to transmit a message. she is going to send a ciphertext to Bob, and then Bob, with his secret, can decode the message. And the security says that if the ciphertext is given to a malicious party, he will not learn anything about the message. So an encryption is non-trivial if the message length is longer than the key length, where you cannot do one-time pad. And in fact, classically, we know anything like this would actually imply the existence of one-way functions. Okay, so now let's consider building a quantum encryption. So everything is the same, but the ciphertext is now quantum. And the goal is to build a one-time encryption of arbitrarily many bits, much longer than the starting key that you are given. So so I claim that this is easy once you have PRFS, because what you can do is to look at each bit in your message. So for example, for the first bit of the message, if the first bit is 0, then you can just send the PRFS state on input 1. Otherwise, you just send a hard random state. And you just repeat this for every bit. And for Bob, what he can do is to decode the message, he can just take every hard random state, try to project it onto the PRFS state because he knows the key. And which is basically means test equality. So if it equals the PRFS state, then he will know that this message bit was 0. Otherwise, he's going to say, okay, it's probably a 1. So it's not hard to show that this scheme is correct with probability like 1 minus something like exponentially small in n. So as long as the PRFS output length is super logarithmic, this is correct, except with negligible probability. And another crucial observation here is that we only fed L different inputs to the PRFS. So as long as the input domain is as large as L, this construction works. And for security, this immediately follows by the security of PRFS, which says that no matter what you are encrypting, all of these states should all look like hard random quantum state by the security of PRFS. Okay, so for big commitment, I think I'm running kind of short on time, so I'll just give you a high-level idea of how we constructed it. So this is the null commitment that we all know how to construct from pseudo-random generator. And it turns out that once you have PRFS, then you can just replace the PRG with a PRFS. So on a high level, what you do is previously you are sending the output of the PRG plus either a random XOR, or you not do the random XOR depending on which bit you want to commit. Here you just prepare the PRFS state so that it's long enough, and then you either apply a poly or not, depending on which bit you want to commit. And then we show how this is hiding and binding. So there are some subtleties. Of course, first, because this is a quantum commitment scheme, what happens if the malicious committer commits to a superposition over two bits? And also, I didn't really tell you, but how do we actually efficiently test whether these states test equality, basically? If you send me a PRFS, how do I actually test whether this is the correct state? So I'm just going to refer you to the paper for these subtleties. So we came up with a new binding definition, and then we also give a testing circuit. Okay, so now I last tell you candidate constructions of PRFS, and why should these candidate constructions be independent of one-way functions? Okay, so the first candidates come from random quantum circuits. So here's an illustration. On a high level, it's just a bunch of random gates applied on two qubits at a time, and then you just repeat this process. So this thing can be described by a classical key, which is basically describing which two qubits you are acting on and then what is the action. So the way that you compute it is you start with the O0 state, you compute this random quantum circuit, and then you just take its output. And the conjecture is that this actually gives you a pseudo-random state. And this object is interesting because this thing has already been studied in various other contexts, including quantum supremacy. Like the experiment that they're performing is exactly on this kind of circuit, but also in the study of black holes. And maybe we can even hope that maybe we can get quantum crypto protocols that can be realizable on near-term quantum devices if we start with this kind of candidate. Okay, and finally, wormholes. So what is a wormhole? A wormhole is just two black holes connecting two distinct regions of space-time, as illustrated here. So the toy model of a wormhole is that you start with an initial state called TFD, and then there is some unitary that governs how the wormhole evolves over time. We denote it as U. And so the construction is that we're going to basically send random particles into the wormhole. Formally, this is captured by a shock, which is a random Pauli operator applied on the first qubit. So you can think of this as some random particles that we're sending into one side of the black holes. So here's the construction. It's basically you start with the state, you let it evolve for a while, and then you apply a shock. You let it evolve for a while, and then you apply a shock. And then these shocks will be the private key for the PRS. And it is conjectured by this work by Gulen, Pepperman, Vazirani, saying that this thing should be a pseudo-random state. And they prove that this is true if you can model U as a random black box unitary. So maybe we can hope that this is secure just from the evidence that black holes are scrambling, and therefore maybe we can use some literature from black hole physics to prove its security. Okay, so these are the two candidates, wormhole and random quantum circuits that I know of. I don't know any other more, but I would love to. But obviously, we right now don't have much formal evidence whether they are secure or insecure, or if they are actually independent of one-way function, although it appears so. And finally, could we even hope that maybe we can achieve better crypto protocols from these candidates? Okay, so to conclude, let me also mention other discussion. So our work really gives a new research direction, which is considering quantum cryptography and their relation with quantum computational hardness. So as I mentioned, there are some output length for which PRS neither suffices for statistical construction or crypto. So ideally, I would like to close this gap. And also, what other interesting quantum hardness lies beyond pseudo-random states? There is an upcoming work that partially gives some solution for these problems. And we also give a somewhat minimal primitive for quantum cryptography. Okay, so that's all. Thank you.
Okay, thank you for this great talk. Do you have any questions? Then please come forward. Yes.
I don't know if the question really makes any sense, but I have given myself the privilege of asking what I call stupid quantum questions, of which there are many. Do errors help with this? If the circuits are not accurate, if there are quantum errors in this, does that help or hurt you?
So you mean, does it help or hurt making cryptographic applications? I don't know. I haven't thought about it much. Yeah, sorry.
Okay, if there's no more questions, I hope to see this black hole implementation next year. So let's thank the speakers of this session again and enjoy your coffee break.